In this lesson, you're going to see the advantage of performing operations in scientific notation. So at the end of the lesson, you should be able to answer the question, how does scientific notation ease the process of computing with very large or very small numbers? So let me remind you of your multiplying and dividing rules for powers with like bases. So for multiplication, if the bases are the same, you keep the base and you add the exponents. Where with division, keep your base and subtract your exponents. So what I'm going to do in this first example is, it's all multiplication. I have two values in scientific notation. By the commutative property, I'm going to restructure this since it's all multiplication. And I'm going to put my powers of 10 next to each other so it's easier for you to see what's happening here. So hopefully you see that we have these two values, and then right here we have like bases. So I'm just going to use my calculator and figure out what 4.65 times 8.1 is, and I get 37.665 times, here I've got like bases, so I keep my base and I add my exponents, would be 10 to the 4th power. Now it's almost in scientific notation, but this value is too large, so I need to shift my decimal point 1 to the left, 3.7665. By doing that, I've actually divided by 10, so I have to compensate by moving my exponent 1 to the right, which would be multiplying by 10. Now, you can certainly try to type all this in your calculator, but what often happens is the values are too large for the calculator. It overloads the calculator and it switches to calculator notation, and sometimes that really confuses you. So doing computations with the values, leaving them in scientific notation, is just easier. Now, with division, I'm going to kind of just focus your eyes by grouping it like this. And again, I'm going to use my calculator to do 2.5 divided by 4.0. And when I do that, I get 0.625. And then here, I keep my base and take my top exponent minus the bottom exponent. So 9 minus negative 7. That would be 10 to the 16th. So again, it's almost in scientific notation, but I need to shift my decimal point 1 to the right to make it 6.25. And by doing that, I have to shift my exponent 1 to the left to make it 10 to the 15th, one smaller. And let me show you now an example of the power to a power rule, which states keep my base and multiply my exponents. So what I need to do here, though, is distribute first this exponent, because I have two factors inside. So I'm going to have 4.6 to the 2nd power, which if I square that, I get 21.16 times 10 to the keep my base and multiply my exponents would be to the negative 8th. Now, I almost am finished, but I need to shift this one to the left to make it 2.116. If I do that, I need to shift my exponent 1 to the right. On the number line, that would be negative 7. Now it's in scientific notation. Okay. This next application question says, the world population is about 7 billion, and there are 4.6 times 10 to the 7th ants for every human on the planet. About how many ants are in the world? It's a lot of ants. So for every one person, there's 4.6 times 10 to the 7th. So if there's 7 billion people, I need to consider what that looks like in scientific notation. So million has 6 zeros, billion is going to have 9. So I know that that's 7 times 10 to the 9th. And I'm going to multiply that. I'm going to multiply the people by the number of ants. So times 10 to the 7th. So I'm going to end up multiplying the 7 times the 4.6, which is 32.2. And I keep... Sorry about that interruption there. So now I'm going to multiply 10 to the 9th times 10 to the 7th, which is keep my base and add my exponents. I'm almost there. I just need to shift my decimal point, which means I'm dividing by 10. And I shift my exponent 1 to the right to make it 10 to the 17th power. So that's how many ants there are in the world. 3.22 times 10 to the 17th. That is a lot of ants. Next question is about social media. It says Instagram processes about 990 billion likes per year. If Instagram has approximately 8.9 times 10 to the 8th users, about how many likes is each user responsible for per year? So let's consider what, goodness, 990 billion looks like. So that's going to have 9 zeros for billion, but it's 990. So if I place a decimal point here, that's going to be 9.9 times 10 to the 11th if I count my place values to get it back to where it was. So that's how many altogether there are, but how many likes per person? So if I take this divided by the people, so the number of likes and the people on the bottom would be 9.9 divided by 8.9 is about 1.11, and I just rounded to the nearest hundredth, times 10 to the third. There it is in scientific notation. This would be per person. In standard, this is approximately, because I rounded, so I'm putting approximately. I'm going to shift my decimal point 3 place values to the right. That's about 1,110 likes per year. Now, if you think about how, if you use Instagram, that is, how many times you hit like each day, this definitely might be on the low end. Okay, so I have a few additional practice problems for you here. You can certainly pause the video and see if you're understanding and just kind of forward the video to see if you're correct. So what I have is another multiplication one where I do, I'm going to do 12 times 8 first to get 96, and then I keep my base for the tens because they're like bases, and I add my exponents would be -8. Got to shift my decimal point to make it 9.6 and shift my decimal point the opposite direction times 10 to the -7th. Number 2 is a division question. 13 divided by 8 is 1.625 times 10 to the, keep my base, and do -8 minus -4 would be -4. This is already in scientific notation. Now, number 3 is mixed between scientific and standard. I'm going to choose to change it to all scientific. I just find it easier to work with. 2.3 times 10 to the 5th power, and I have 5.4 times 10 to the 7th. So I'm going to multiply 5.4 times 2.3 on my calculator, and I got 12.42 times 10 to the, keep my base and add my exponents, 10 to the 12th. Now I've got to switch this because it's not quite in scientific. Be 1.242 times 10 to the 13th. Number 4, again I'm choosing scientific notation. You could switch it to standard if that's your preference. So the bottom would be 4 times 1, 2, 3, 4, 5 times 10 to the -5th because I had to move it in the negative direction. So 9 divided by 4 is 2.25 times, keep my base, take my top exponent minus my bottom exponent. So 3 minus -5 is +8. And there it is in scientific notation. Number 5 is an example of a power to power rule. Another practice one, so I'm doing 2.13 squared would be 4.5369. Now sometimes you'll see that rounded to 2 decimal places, but I'm extending it to all 4, not rounding at all, times 10 to the -16th, because power to power is keep your base and multiply your exponents. So it's in scientific notation, so there it is. So hopefully you see the advantage of leaving values in scientific notation to do computations.